Look at the floor of any modern warehouse today. You'll see autonomous mobile robots effortlessly threading the needle between scattered boxes and dynamic traffic. The software driving those machines is iterating so rapidly that relying purely on physical hardware for every test run is a liability. It is too slow, too expensive, and often unsafe. Simulation has become the mandatory default starting point for engineers because modern development moves faster than real-world testing can safely support. But the market is flooded with options. Selecting the wrong one turns your robotics team into a software configuration department, drowning in environment setup rather than tuning code. A mismatched simulator stalls your actual hardware timeline, turning a 3-day integration into a multi-week troubleshooting project. When evaluating your options, you usually face two extremes. On one end, overly simplistic 2D tools. On the other, highly complex environments built to generate bleeding-edge synthetic data. Let's map this out to see where a tool like Webots fits in. Webots has become a go-to middle ground because it offers realistic physics without the crushing setup burden of high-end research platforms. You have your 2D kinematic tools, offering low effort but low fidelity, and you have heavy rendering engines, demanding massive effort for high visual payoff. Webots sits right here in the sweet spot. It prioritizes rapid iteration and approachability over absolute visual perfection. It provides a highly credible baseline for testing complex physics and control logic, and it runs reliably on standard developer laptops. In practice, robotics teams are rarely uniform. You have researchers on macOS, control engineers on Linux, and operations staff on Windows. Friction occurs the moment a simulator forces an entire team onto a single operating system or a single programming language. Webots bypasses that friction entirely. A computer vision researcher can prototype a perception model in Python, while the core engineering team writes performance-sensitive controllers in C++ right next door. This flexibility is essential for maintaining a digital twin, a virtual counterpart that stays aligned with your physical hardware throughout its development lifecycle. A practical digital twin remains useful only if the team can easily update it on a weekly basis to match the physical robot's evolution. Because anyone can run the software natively, multi-day IT troubleshooting is replaced with immediate collaborative programming. That iteration cycle must account for reality. A slight wheel slip on a dusty warehouse floor causes a purely kinematic simulator to fail immediately. Webots handles these edge cases by modeling rigid body dynamics. You can identify physical design flaws, like a top-heavy center of mass tipping a payload, before you ever build the prototype. Once the physics are solid, you need to connect your software. Today, ROS2 is the standard middleware for routing data in production-ready autonomous systems. Healthy engineering separates software from hardware, so disconnected sensors won't crash your logic. Webots acts as the world layer, generating simulated sensor topics. Your ROS2 navigation stack plugs directly in, letting you test planning and obstacle avoidance as if it were a real machine. You can safely tune your cost maps and evaluate your recovery behaviors, figuring out exactly what the robot will do when it gets boxed into a tight corner. This hardware-agnostic architecture lets developers ruthlessly stress test their autonomy logic without risking a $50,000 piece of hardware. Modern autonomy is also leaning heavily into AI. Engineering teams are embedding learned models directly into their stacks for tasks like semantic mapping and complex terrain classification. Training these models, especially through reinforcement learning, requires running thousands to millions of repeatable experience loops before the policy converges. Webots supports this scale because it includes highly credible simulation for core inputs like LiDAR, stereoscopic cameras, GPS, and IMUs. The environment becomes a computationally lightweight dataset factory. You can instantly generate severe edge cases, unusual warehouse lighting, occluded sensors, or rare mechanical failures. Generating this specific data synthetically ensures your AI models will survive unexpected physical variables, and it does so without requiring a massive, expensive GPU farm. Selecting the right simulator depends entirely on matching the specific strengths of a platform to your team's project constraints and existing hardware. Here is how to map that decision. If your project relies heavily on legacy ROS ecosystems and requires deep plug-in customization, Gazebo is the necessary choice. If you are an enterprise team building massive, photorealistic synthetic data pipelines for computer vision, you should invest the GPU power into NVIDIA Isaac Sim. But for rapid iteration, ROS2 navigation prototyping, and mixed team environments, Webots remains the most accessible starting point. Making the right selection here prevents critical delays and aligns your software environment directly with what you are actually trying to build. Once you commit to Webots, treat it as a rigorous engineering environment. Start with basic navigation and gradually layer in complexity, like dynamic obstacles and sensor noise, rather than building the entire world at once. Ensure your virtual sensor placements and update rates perfectly match the physical robot's eventual hardware mounts. An optimistic frame rate in simulation will hide severe bottlenecks. You must relentlessly test recovery behaviors. Watch how the logic handles failure states when navigating through a restricted physical choke point, like a cluttered doorway. Build a standard known baseline test world and run it immediately after every major code change to ensure you haven't broken your core navigation. Successful sim-to-real transfer relies on building robustness against noise, ensuring your code functions across the unpredictable variables of the physical world. Standardizing your workflow around a pragmatic, reliable simulator like Webots allows your engineers to confidently bridge the gap between their initial code and a safe, physical, autonomous machine.